Again, welcome to the 2018 NI lecture. I am Laura Koenig. I am the president-elect for the Cryosphere section. We would like to welcome you to this event. Tavy Murray, the current president, sends her warm regards, pun intended, from Antarctica. And I would like to introduce you to Michelle Copez, our president-elect, soon to be president-elect on January 1st of this year. Thank you. Thank you for joining us, and welcome to AGU 100. We've been planning for the centennial for quite some time, and it is finally here, and it is time to celebrate. Your Cryosphere section has been a leader, and we thank you all for your participation in celebrating AGU's centennial through AGU narratives and many of the events that we will have planned coming up this year and at this conference. Hopefully you've been able to participate in some of those, and I will highlight them in my slides shortly. I'm proud to say that the Cryosphere section has been one of AGU's most active session in supporting AGU 100 activities. Through our Cryo Gives 100, contribute to our legacy. Through Cryosphere Gives 100, we are encouraging all of our members to donate $100 to the Cryosphere section and or 100 minutes of your time, or both, to AGU-specific events this year. Oh, I'm hitting the wrong buttons. If you need some ideas on how to spend your 100 minutes of time, we have our Give campaign, again, to give $100 or 100 minutes. We have policy events that are scheduled throughout this meeting where you can write letters or go and visit your congressman. We will also be providing through the Cryosphere AGU website some letters. So if you want to write your congressman or local representatives after, we'll give you some templates for which you can do that. We've had cryo mentoring. If you see anyone with the cryo mentor or mentee tags, we've met up for cryo coffees. And are getting to know more people within our section. We also have opportunities for you to come and listen. Just after this session, we'll have the 100 Years of Cryosphere session. There is a 60 years of scientific achievements in Arctic and Antarctica, and there is a centennial plenary, which will be a whirlwind of all of the science that AGU does in 2 hours with 4-minute talks on Friday afternoon. So try and participate in one of those events while you are here at the 2018 meeting. Cryo Gives 100 through 2019. We have taken on a few initiatives that we intend to complete this year. For education and outreach, we are looking to compile 100 minutes of your best YouTube videos that relate to education and anything that's Cryosphere. We will be compiling those on your websites. Watch for more information as that comes out. We will also be reaching out through what we are going to call our 100 Faces, 100 Places, 100 Years initiative. This is where we will be compiling your photographs of things that have happened within the Cryosphere. As I say this, I'm going to encourage you all to open your emails specifically from Tavy Murray or myself over the next year. These are the emails that are Cryosphere specific. I know you all get a lot of emails from AGU, and it is hard to keep track of which ones to open and which ones to auto-delete. The Cryosphere section has been very proactive. We have a lot of early career and student members who have started compiling our newsletter. These will be less than 10 tweet length bullet points of things that you should know that are going on at AGU. Please read those and look at those so you know what's going on with our section. Things that are going on that are always ongoing that our section supports are our business meeting and reception. That is this evening. We usually do the early career, early open event before our reception. That will not be held this year. That is only due to the venue here in Washington, D.C. Thank you all for being flexible in our new venue, but we will not be hosting that early career event this year. It will happen again in 2019 when we are back in San Francisco. And please come out on Thursday evening for the Flash Freeze event. This is when our students present very short 3-minute flash talks to win one of 5 $1,000 scholarships to continue their research. I want to point out our executive committee members that are doing all of this great work for our section. They are wearing stickers on their badges, so get to know your executive committee members, and I want to thank all of these people for their service to our section this year. I also want to give a big thank you to Tavy Murray and Sinead Farrell, our current president and secretary, who will roll off on January 1st, 2019. Thank you all for the work that you have done. I will also say that Sinead has been instrumental in pushing forward our website. You can go to our website now and see pictures of all of the executive committee members. So when you want to know things that are going on in our section, you can find their faces there. And again, welcome to our new members, Michelle Copez and Peter Neff, who is also in Antarctica. He will be our new section secretary. Please engage with us at AGU. You will see that we have upped our presence for AGU Cryosphere on Twitter and on Facebook. And we also, again, send out those newsletters. AGU Cryo took over the Insta feed for all of AGU to promote cryospheric sciences leading up to this. And many of our sessions, including this one and the 100 Years of Cryosphere, will be live tweeted. And for our panel discussions in the 100 Years of Cryosphere, we'll be able to take questions over from both the audience and for the section. And from the social media. So please submit your questions over social media. And now to begin our award presentation. So our Early Career Award honoree this year. Our Early Career Award honors significant early career contributions to cryospheric science and technology. It has been awarded this year to Dr. Ludovic Broker. Do forgive me, I have spent enough time with Ludo that I will refer to him as Ludo as opposed to Dr. Broker. Ludo is a scientist and manager for the University Space Research Association's guest star group within the Cryospheric Sciences Laboratory at NASA Goddard Space Flight Center. During this, our centennial year, as we contemplate our past of exploration and discovery and envision our future of diverse research, technical advances, and improved models, Ludovic's research truly embraces this moment. With scientific achievement spanning multiple subdisciplines using traditional field methods and basic discovery alongside sophisticated remote sensing techniques and modeling analysis, his body of work and more than 40 peer-reviewed papers, months of Arctic and Antarctic research, and leadership roles to advance remote sensing within NASA missions, developing publicly available data sets, algorithms, and models for snow accumulation, sea ice extent, and ocean salinity has advanced glaciology and cryospheric sciences. Ludovic's work has touched on almost every subdiscipline within our field, with the exception of permafrost. So he has about 20 years to publish within permafrost. As I mentioned before, I have worked with Ludovic in the field, and I want to add that his excellence in science stems from his diligence and hard work. His work ethic is evident in his innovation, diverse and excellent science, and the fact that he is always the first one up in the morning making coffee on any field expedition, and he is the last one in the tent after a night of shoveling. Please join me in congratulating Dr. Ludovic Broker, our 2018 Cryosphere Early Career Award winner. I look forward to his talk, Microwave Remote Sensing of Snow Advances Over Ice Sheets, Land Ice, and Sea Ice.
Well, thank you very much, Laura, and thank you everybody for those kind words. I won't say it enough this week, but I'm really happy, and I'm thrilled about sharing this recognition with all my co-authors and collaborators over the year. I've been very lucky because I got the privilege to work with outstanding people who care for ethics and strive for quality. So they have been my mentors for years, and today this is the recognition for my mentors. So thank you very much to them. Thank you. So I'm employed by USRA, which is a non-profit association working for NASA, and I'm affiliated to the Cryospheric Sciences Lab at NASA Goddard, where I work on microwave remote sensing of snow of the different components of the cryosphere. And my overall objective is to create data sets for you so that you can study changes, you can assess the impact of those changes and go all the way up to policies. So how do we study changes over the cryosphere and the vast polar regions? There are many complementary approaches. I list 3 over here. Weather station or in situ measurements, typically everything that will give you direct in situ measurements of a geophysical variable. The downside, though, is that it's a local measurement and that it requires some human presence, at least at times during the year. An alternative to that is regional and climate models. Okay, the models give us a full spatial coverage and a very fine temporal resolution. We have access to a high number of variables. However, the quality of the result does depend on the quality of the parameterizations, which may be more or less theoretical and therefore more or less appropriate to the study area. The last method I mentioned here is remote sensing. Of course, that's the one I use the most. Satellites give us a good spatial coverage, and overall one of the best assets is that it's a measurement. However, it's an electromagnetic property that is measured and not a geophysical property. So, and that's my job, is to go from one to the other. There are many types of remote sensing techniques, active, passive, with instruments working at different frequencies. So I will start with passive microwave. Those sensors, radiometers, listen to what the Earth or the ice emits and is scattered by the snow cover. So typically over an ice sheet, the radiation does depend on the temperature profile and the snow microstructure properties. So what I really want to make clear on this slide is that the radiation emanates from under the surface, propagates through every snow layers, and therefore the radiation does carry information about the snow properties as it's moving upward towards the surface and then all the way through the atmosphere up to the satellite. So my job is summarized on this schematic. It's really to relate the snow properties that we measure in the field and their impact on the signal measured from a satellite. So I've done that over ice sheets. Typically, that's an ideal scenario for us because ice sheets are thick, therefore they can be assumed as semi-infinite. Changes are typically slow, occurring mainly at the surface, and the field of view is quite homogeneous. When we try to do that over terrestrial seasonal snow, then some challenges for sure are added. Now you have to deal with a substrate, a soil, that does vary spatially. It also varies during the season. Its states for sure change from thaw to frozen. And in the field of view, you start to have some diversity and heterogeneity with lakes and vegetation, of course. And to go even one step further, and I won't talk very much about it today, it's sea ice. I will leave this to Ron and Jackie. But sea ice, in my view, is even more complicated because it moves, it cracks. Suddenly you have open water that is exposed. Ridges can form, and that will dramatically change your roughness. And one thing we don't do very well, I think, at the moment is to account for the impact of brine, of salinity inclusion in the snow, because this impacts the microwave radiation as well. So to keep it simple today, I will present a time series of brightness temperature, denoted as TB. This is over Antarctica at Dome C. It's a 15-year time series that you see in red, and the black time series is the air temperature. So those two time series are actually well correlated. The brightness temperature variation occurs in phase with the air temperature variation, therefore with the snow temperature variation. However, those two time series are very different. They have different levels, and the amplitude of the brightness temperature variation is smaller than that of the air temperature variation. And this is the impact of emissivity. So emissivity depends on liquid water when the snowpack is wet. Otherwise, it will depend on the snow microstructure properties. And it also depends on some observation characteristics. So this example is to show that when you understand the emissivity and the properties controlling the penetration depth, we can relate the brightness temperature to some snow properties. And that's what I will try to show today. So first I will show forward modeling result. In this case, the snow properties have been measured and used as input of a state-of-the-art radiative transfer model. It's named DMR-TML. It has been repackaged under SMRT. And from that model, we can obtain the black time series, which is a simulated brightness temperature, and we compare it to a satellite observation. And you can see the result works very well. That, to me, was an exciting result. We obtained an RMSE less than 1 Kelvin. So such a level of result was possible to a new approach, a new idea at the time to quantify microstructure. Instead of arguing what is the relevant size of a crystal and how it should be measured and so on, we used a profile of reflectance, of near-infrared reflectance, from which we derive snow-specific surface area. And that was used as input of the model to produce this results. So I realize this is exciting to me, who consider remote sensing as a science and not as a tool. But for the AGU community, I understand that instead of brightness temperature, you would much prefer to have a geophysical variable shown on that plot. So once we know that we have a good model that performs well, we can start to do some inverse results or inverse modeling, which I will show now. So you can see on the screen 2 maps of emissivities in Antarctica. It's only on dry snow, so ice shelves have been masked. And we will hear from Helen in the next presentation about changes occurring on ice shelves. These 2 maps are different frequencies, and overall, hopefully, you can see even from the back that the spatial patterns look quite similar on the 2 figures. So what can be done is show those emissivities on this scatter plot. On the x-axis, you have the emissivity at 19 gigahertz as a function of the emissivity at 37 gigahertz. Each black dot does represent a pixel. And what's striking is that the emissivities are mainly distributed along the one-to-one line. So you could ask me the question, well, which snow properties can explain such a distribution? If we consider a snowpack that has no increase in grain size, so it's exactly the same size from top to bottom, simulated emissivities will follow the blue line. You can see the blue curve on the left, and the annotated values are the grain size at the surface. So clearly, they do not explain observed emissivities in Antarctica because they are far from the one-to-one line. If we now increase grain size with depth, okay, emissivities will suddenly follow the red dashed line here and will migrate toward the one-to-one line. So that's for one surface grain size, and we increase the grain size with depth. We can do similarly for a larger grain size at the surface, and we can cover the entire domain. And the beauty of that approach is that to explain a black dot on the screen, which is a pair of emissivities at 19 and 37 gigahertz, there only exists a unique pair of near-surface grain size gradient. Therefore, it's almost straightforward now to go from those 2 maps of emissivities to these 2 maps of grain size profile parameters. You can see on the left the near-surface grain size, and on the right the grain size gradient. So at the time we compare those results with in-situ measurements, and we have looked at 2 regional models, RACMO and MAR, who can actually reproduce the grain size growth. And the spatial pattern were similar thanks to accumulation and temperature and so on. So I've chosen this example and decided to share it with you today because it's rather easy to explain and it's simple. We have been lucky that only 2 parameters can be explained with, or two observations can be explained with 2 grain size parameters. However, as I said in introduction, working on ice sheet is rather simple. As soon as you add more challenges and complexity, like for seasonal terrestrial snow, then you need to consider more observation than the 2 frequencies I've used here. So I'm transitioning now from those 2 studies that I've published very early on, 10 years ago, to what I've done last week in support of SWISAR. So SWISAR is an airborne prototype instrument that is developed at NASA Goddard. It's named a Snow Water Equivalent Synthetic Aperture Radar and Radiometer. And truly the innovation of that instrument is that it uses a single antenna. And hopefully you can see it on the right-hand side. It's rather, where is the pointer? That's what I needed. That's the antenna right there. So it's very small, and it's a single antenna for all the frequencies that are used. There are 3 frequency bands for the radar and 3 different frequency bands for the radiometer. So you can get an idea of the size of the instrument. It flew on a twin otter over Grand Mesa last week. Those were the first engineering test flights, and overall it went extremely well. I was pleasantly surprised. I've done some field measurement there with Chris Yemstra last week. We collected about 1,500 depth measurements and some snow pit as well. So you can see the plane flew over our ground tracks. I will show some preliminary results of the radar. I think it's important to communicate about it, and I will explain later on why I think it's wise everybody see those results today. Those images are, again, preliminary results, are not geo-referenced, are not geo-corrected. It's over the Grand Junction Airport, so you can see here is a parking lot. This is one open field, and if you see any bright spot in that open field, those are corner reflectors that will be used to geo-calibrate, geo-reference and calibrate the radar later on. So this is at X-band co-pol, same thing at cross-pol. As I said, there are 3 frequencies, X-band, and there will be a KU low that you will see now, and KU high. As we go higher in frequency, you will see that the swath here reduces. We have a requirement of 200 meters, which was met last week during the flights. So those were test flights near the airport, and now I'm showing just one image randomly selected on the Mesa. So remember, Mesa last week had some snow on the ground, about 50 centimeters on the west side, and there are many sagebrushes. And actually, hopefully, you can see from the back, it's not at all a fuzzy image. All the dots you see over here are actually sagebrushes that are snow-covered. This is a lake, and here you can see also some stream and likely some water that froze on the ground over here. So I will just burst through the 3 different frequencies. It's, as I said, very exciting to see this kind of result only a week after operating a new type of instrument on an aircraft platform. KU low again, and I apologize, it's me who did the cropping, so I just tried to align the images. Nothing to worry about though. And now at KU high. So why I think it's important to show those results today, it's because there is a lot going on at KU band nowadays. Hopefully for SWISA, the next step is to fly in February as part of NASA's SNOWX mission. So it will be a coordinated campaign during 9 days. Mid-February, that will include about 20 people on the ground. So feel free to join the SNOWX town hall meeting on Thursday that will be led by HP Marshall. And of course, we will have to test now and enhance some retrieval algorithms. There are many presentations that were given yesterday on that. So here is just to illustrate what would be a typical change in both backscatter and brightness temperature as a function of snow-water equivalence. So now instead of the 2 frequencies I've presented earlier, suddenly we have 9 additional observations that can be utilized to constrain the retrievals. The Canadians are also working on KU at the moment. They have proposed a KU low and KU high snow mission that has been accepted and is now in phase 0. So University of Massachusetts is operating one of their single KU band radar over Trail Valley Creek. So they started in October, and they will continue that mission until March. So there is a good momentum in Northern America to utilize that frequency. So any time that is spent studying those frequencies and investment contributing to relate KU band observation to snow water equivalent is actually, in my view, a good investment in time for the coming years. So that's what I hope to present today. I won't give any scientific conclusion. I will just give some takeaway points that I've noticed and was beneficial for me, that remote sensing and field work go hand in hand. Clearly, it's a chance for me to go in the field, but I think it's actually critically needed. You can't claim to retrieve anything from a spaceborne or an aircraft platform without measuring it on the ground. And of course, working on ice sheets, terrestrial snow, and sea ice has been highly complementary. It has been very stimulating, not always easy, but I've noticed that from at least a modeling perspective, you can just swap the substrate, and still it's the same physics that is applied, and the same tools and techniques. And today, thanks to this, I can definitely say that it has been a very rewarding experience. So, thank you very much, everybody, and thank you again.
And is there a question?
So right now it's an airborne prototype instrument. There is a path to space, so frequencies utilized by SUISA are allowed frequencies. The antenna that I've shown is very small, so you can still make it much bigger and put it in space and obtain a fine spatial resolution. Right now from the airborne platform, flying at about 2 kilometers elevation, we can get a 1 by 1 meter resolution on the ground. Thank you.
Great, thank you. And I do actually just want to remind everyone that a few years ago we expanded the NI lecture to the NI lecture with special guests. As the cryosphere shrinks, our cryosphere section continues to grow, and we want to make sure that we highlight the diversity across our field. So our special guests are always our early career lecturer, or our early career awardee, and the fellows who were elected at the last meeting, which brings me to our next talk. Dr. Helen Amanda Fricker from Scripps Institute of Oceanography at the University of California, San Diego, was elected a fellow for the Cryosphere section in 2017 for advances in our understanding of Antarctic ice sheets, ice shelves, and subglacial hydrologic systems. Helen has served our community as a prominent scientist, leading to the discovery of active subglacial lakes. She has worked with NASA missions and has served as a leader for multiple scientific organizations, including serving as a past president for AGU Cryosphere section when it was called the AGU Cryosphere Focus Group. I look forward to Helen's talk. Short-term changes in Antarctic ice shelves are key to predicting their long-term fate. Please join me in congratulating Dr. Helen Fricker for her induction as an AGU Fellow.
Thanks, Laura. That was a very nice introduction. Okay, so my talk is going to follow on really nicely from the previous one, which is great because I didn't know anything about the previous one. But basically talking about how we really need to use satellite data and ground-based data together to understand how ice sheet systems work. So I do get funding from NASA and NSF, and that's how it works. And it's not really awkward when you see both program managers because they get it. So first of all, I'm revealing the new logo for the Scripps Polar Center. I'll tell you about that at the end, but I thought it looked very beautiful with this photograph, which was taken by Jeremy Harbeck during the Operation Ice Bridge mission over Getz Ice Shelf. So I'm going to talk about mainly about science, but I'm going to talk at the end about some other things to do with AGU and things that are changing in cryo, which is awesome. So today, there's a lot of people involved in this work, and they're listed here on the bottom right. The person who's not listed on here is Laurie Padman, because they wouldn't let him be an author, because he's not at an academic institution. We need to change that at the conversation. For those of you that don't know, the conversation is a really nice way of getting your science out there to the public. You get to work with an editor. They help you write your story in a way that makes sense, which is for the public, which, as we all know, is very important at the moment. So we worked quite hard on this article, the 5 of us, actually 6 of us, no, 5 of us, Laurie plus 4. And we came up with our storyline through all the work that we've been doing. So I'm just going to walk you through some of that now. And then we will get to some other things. So I think we all, as Jonathan Amos from BBC says, everyone loves a big berg, right? Everyone loves a big iceberg. And it's true, they do. But you do need to remember that icebergs carve on a basis that is, it's a background sort of rate of change. It's not a, hey, the whole world is falling sort of thing. It's dramatic, it's eye-catching, but we do need to keep this in context. And we need to really understand how the ice shelves are changing on a long-term, multi-decadal timescale, so we can really get a picture as to what are the major things in place. So with that in mind, let's just back up and remind ourselves why ice shelves are so important. So I know this is a very broad audience. We're just going to have a little bit of Ice Shelf 101 here. So Antarctica's ice shelves, they sit all around the edges of the continent, and they gain mass through snow accumulation, and they lose mass through these processes, mainly mainly basal melting and iceberg carving. And this is essentially how these ice shelves stay in balance. And the reason why they are important to the ice sheet, the grounded ice sheet behind it, is that they actually act like a buttress. They're sort of literally pushing back on that grounded ice like an architectural buttress, and they're stopping that grounded ice flowing to the ocean. So once you shrink an ice shelf, you're actually going to allow more grounded ice into the ocean, and therefore sea level rise will go up, and that will affect us everywhere, all around the world. This is a cartoon that we drew for a paper that we have in preparation with Hilmar. Now, Hilmar is going to talk about this tomorrow, so I'm going to advertise this. This is modeling the effect of grounded ice, the thinning ice shelves on grounded ice. So I encourage you to go to that talk tomorrow to find out about that. So looking at the ice shelves, this is work all done at Scripps. Hamish came to Scripps to do the one on the left, and then Fernando was my student, and then postdoc, and now he's at JPL. And this is looking at thinning rates on Antarctica's ice shelves from two different instruments. The one on the left is a shorter period for NASA's IceSat, and the one on the right is a longer period with 3 missions stitched together, going from 1994 to 2012, 18 years of change, nearly 2 decades. And so from this, we see a picture of mass loss from the ice shelves, mainly concentrated in the West Antarctic, as we know, where those red circles are wider, or larger. That means that it's more mass loss. And we're seeing the Amundsen Sea and the Bellingshausen Sea is where we're losing most of the mass. And overall, we know that where we're losing where the ice shelves are thinning and we're losing mass there, we're actually also seeing changes in grounded ice. This is an attempt at morphing these two studies together. This is Hamish's study on grounded ice, which I was not involved with, and then this is the ice shelves from Fernando. So you can see red matches up with red, basically. Loss is loss. And Fernando had another paper which is on the methods, which some of you might not have seen, and this is talking about looking at the changes, just looking at West Antarctica, East Antarctica, and then all together. And we can see that mainly what we're seeing for all of Antarctica is dominated by what's going on in West Antarctica, where there's a long-term loss. In East Antarctica, there's a little bit of a gain at the beginning, which is increasing snow accumulation during that time. But over the second half of the record, we are seeing also a loss. So the reason why this is all important is because the sea level potential of Antarctica and all that grounded ice added up is very large. If you add up all the drainage basins, this is a plot that my postdoc Cyril Mosbo did, and it's looking at all the drainage basins and their sea level rise equivalent. So the darker blue is lots of sea level rise. We should worry about that, 12 meters. And then the lighter blue is less sea level rise. We should still worry about it, but it's not so large. And the major thing you can see from here, that East Antarctica is the big thing. It's the big elephant in the room, the sleeping giant, whatever you want to call it. And we do have hints that things are starting to change. There was a press conference yesterday by Catherine Walker and Alex Gardner, and I've just been on sabbatical at IMAS, and we know this area is somewhere that needs to be, our attention needs to be put there. We shouldn't just go to where we know it's changing. So this is definitely something that we keep in mind all the time when we study these systems. So if you add up all of this together, the total sea level in Antarctica is just under 60 meters, and to compare, Greenland is around 7. So at the moment, this is important because land ice is currently, well, it's the largest contributor to sea level rise, and it seems that its contribution is increasing. So thermal expansion and land ice are the two main components of sea level rise, and we're seeing that the addition of land ice is becoming more and more important, so we need to keep an eye on these ice sheets to understand how sea level is going to change all around the world, because that will affect us all. So back to the ice shelves now. This is a very busy plot, but the point is that I want you to see the interannual variability in these data. These data actually weren't published, but Fernando showed them a few times. And this is comparing for all the different ice shelf regions in West Antarctica, the long-term trend, the 18 years that I talked about, and then the trend from NVSAT, which is just the radar altimeter for the period of IceSat, and IceSat. And apologies if you're red-green colorblind. I didn't do this on purpose. It's actually Fernando put these colors up. I think he did. Anyway, so where you see these lines are parallel, you can see that the laser and the radar altimetry are pretty much in agreement. But you can see we have some work to do because there are some places where we have lines that are intersecting. Is there a laser pointer? Yes. Okay. Oh, great, thank you. Yeah, like, for example, this one here. And East Antarctica, it's a bit messy. Some of these glaciers are really small. The surface is really crevassed, really messy. Some of the radar altimetry has a really hard time with that. We can't do much about it. That's what these systems are like, and we're trying to do the best we can with the instruments that we have. But the interannual variability is super interesting, and what that does is it tells us, it gives us a hint at some of the processes that are taking place on the ice shelves, so we can really try to unravel what's the role of the atmosphere, what's the role of the ocean underneath, how are we changing these ice shelves, and what's actually driving those changes, and we can really then maybe predict what might happen in the future, which is kind of like the holy grail of this work. So along came ESA's, the European Space Agency's Cryosat-2, and it has provided a time series that extends us past that 2012 period. I have to say, European Space Agency are fantastic at getting their missions, so they're continuous and they overlap. It's really wonderful for those of us that look at these ice sheet systems. And so now we have data going all the way to pretty much the present day, because Cryosat-2 is up. Don't worry, I'm going to talk about ISAT-2. That's coming. Okay, so what we've done with this is another work led by Fernando, and this is looking at the time series just all around West Antarctica, and we can see that especially in the Amundsen Sea, this is a pattern of where the influence is strongest. There is an ENSO signal, so we are definitely seeing a link between El Nino and La Nina on the ice shelves, and this is actually the first time this has ever been shown on Antarctic ice shelves. This paper came out at the beginning of the year in Nature Geoscience. And what you can see is that you have a pattern of increased snowfall and basal melting during the El Nino event. And what that does is it actually ends up taking mass away from the ice shelf. It's to do with the density that at the base is higher. You end up increasing the height of the ice shelf, but you decrease the buttressing force. So this is really interesting during an El Nino event, and then the opposite occurs during a La Nina event. Okay, so we have a couple of strong events that we can look at and unravel that. So this is something, sort of watch this space for further work on that. Larsen Sea is another really interesting place in Antarctica, because it's the part of Antarctica which is further north. And so it's affected very much by the atmosphere. And Larsen Sea is the next in line of the ice shelves that have collapsed. Larsen B collapsed in 2002. So people think that maybe Larsen Sea is sort of under threat. So we put together all the time series of data from ERS-1, ERS-2, MVSAT, and Cryosat-2. And also Icebridge flew over the ice shelf as well. And what we see is a thinning up until around 2010 or so, and then we do see a rise again in surface elevation. And this was published as well this year in March by my student Cecile Adesmili. And he linked this, and we worked with Laurie on this. We linked this with a change or a cooling in the region, and this is something that's been documented by other people as well. So the point being here, just to show you that we're now really getting a handle on, now we have a long time series, we can really look at these processes that are occurring on sort of decadal timescales, and we can unravel that from the data to understand which processes are most important on which ice shelf, because each ice shelf is affected by different combination of processes. We're moving into getting into time-varying basal melt rates now, adding Cryosat-2, and this is a paper that Cecile presented yesterday, so I won't dwell on it. I'm sure you were all there. Well, the room was tiny, so I don't think so. But anyway, we're now getting, hopefully, what the modelers need, and this is for comparison basal melt rates from Iterate Rinyo for a shorter period, because they're based on ISAT. And you can see this beautiful variability here, which is hopefully going to provide all sorts of information for people to learn from. Rosetta Ice, I have to talk about Rosetta. There's a poster today. I'm going to show you a picture of the poster because it's absolutely beautiful. Rosetta is an NSF-funded project looking at the Ross Ice Shelf. It's the largest ice shelf. It's the size of Spain or Texas, depending on where you come from. And bathymetry under the ice shelf has been beautifully revealed now, and even more beautifully revealed by Kirsty Tinto, because look at that scarf. I mean, it's just amazing. So she's up there at this poster, maybe not right now, she's probably here. Okay, and one of the things that we did during the Rosetta project, which was really nice for me, because it was getting into some oceanography, which is very exciting, was we launched these airborne launched floats off Ross ice front. I'm hoping that the video doesn't play because it's really loud. I'm just going to run through it. Okay. And this gave us a really nice picture. Even just in 6 places along the Ross front, we got some oceanography information, which is telling us about water masses underneath the ice shelf and where we might expect to see change occurring, things like that. This paper is in revision. Okay. ISAT-2, we had to talk about ISAT-2. So ISAT-2 launched in the middle of September. It was an incredibly exciting time. I have the privilege of being on the ISAT-2 science team, along with some other wonderful, it's just fantastically collaborative group. It's really great. Alex is here and Sinead. And it's really, and Ron is speaking right after me. He's also he's going to show some results. I wanted to just show a couple of really nice results from this mission, sort of first light. This is a sketch that was done by one of our artists. She also did a sketch of myself and Laurie Magruder, our wonderful science team leader. This is a really amazing website. Check this out if you get a chance. Okay, Ben Smith showed this today. It's the first couple of weeks of data over Antarctica. We're seeing some, obviously, beautiful information on topography because ISAT-2 provides really unprecedented spatial resolution by the fact that you actually get 3 for the price of 1 ground tracks as you move along individual satellite tracks. So we can talk more about that afterwards if you're interested. I haven't got enough time to go into it now. But this is the sort of information that you get. The ice front, this was actually a very funny thing because we realized that the Ross ice front was actually on the ISAT-2 poster for years and years before it launched. And then along it comes over the Ross ice front, and this is my student Maya is looking at these data in Rosetta, and she pulled out this plot, which is 1 pass of ISAT-2. So here we go, the 3 tracks here along 1 pass, and we can see this information at the front, which is really nice. It's telling us about processes going on at the ice front. There's Maya presenting her poster. This is today, so you can go and check that poster out. It'll be up till 6 o'clock, I'm sure. This is Basal Channels, more resolution of features that we need to understand under ice shelves. We know that basal melting is pretty concentrated in these basal channels, and ISAT-2 is going to reveal the detail beautifully. This is kind of the hey wow of the mission. This is the ooh-ah part. I think this is going to be transformational in all sorts of applications, but especially mapping coral reefs and how they're changing. And nearshore bathymetry in clear water is being resolved down to about 30 or 40 meters. This example over here these are pretty contrasting examples. This is kind of where you want to go diving. Bikini Atoll, beautiful lagoon floor. This is where you really don't want to go diving. But anyway, this is actually Adrian and Alex are sitting next to each other. So Adrian and Alex right here, bathymetry. So yeah, keep an eye on these. Have to mention Salsa. This team is presently in Antarctica. They just got there. This was tweeted today, or well, yesterday probably. And Matt Siegfried is leading a geophysics team doing EM data. This photograph was taken a couple of days ago. They are about to drill into a lake. The lake was discovered with ISAT data. That was, Laura mentioned that at the beginning. And it's really nice. They're taking a hot water drill and they're going to collect samples, and it's very interdisciplinary project. So we're going to have some very nice information about what goes on underneath lakes and why. Okay. Last few minutes, I just wanted to spend a bit of time talking about why I'm standing up here. I don't know, there's lots of early career people here, lots of young female scientists here, so hopefully this is going to give somebody some inspiration that this honors ceremony was kind of a big deal. It was really amazing. I mean, if you get a chance to go to the one tomorrow night, it's super fancy, fantastic. You get to celebrate all these like incredible colleagues that we have. This is me, and I was very lucky because Robin Bell was the one that was on the stage to present me with my medal, which I forgot, but I did bring my New Orleans replacement medal instead. It was an incredible occasion, but there I was on the stage, and I was one of 6 women. That was it. The gender distribution among AGU fellows is abysmal. It's just shocking. I mean, people, when you tell people, they just go, really? You're like, yep, that's true. So these are the statistics from 2015 to 2018. So this year, actually, it's pretty good. 13 women, that's quite nice. But we are sort of right down there in the 12, 13, 14% level. And we have to do better. So I actually put out a little plea last night on the Earth Science Women's Network Facebook page for some data on this, and somebody found me this article. And look when it was written, 1994. That's the year I started my PhD. So we really haven't done much better since that. In that whole 25 years, we haven't made that much progress. We're still talking about this. But I really think that things have changed. I mean, things have changed a lot. We can do a lot of things. How do we increase, this is actually still true from this article, how do we increase the numbers and visibility of female scientists at AGU? In the cryo section, we're actually doing really well. I mean, Laura mentioned a lot of things that are going on. The cryo mentoring is awesome, even though I only just found out about it and just signed up last night. Sorry, I didn't check my emails from you. I'm just so sorry. But you really must, because it's very important. I think the single most important component for keeping women in the professional ranks is still to observe female scientists up here on the stage. And actually, it's pretty amazing that all three of us up here. Okay, so how do you do that? You ask for a talk. I know it's really easy to hit the poster button. I know it's super scary to be up here. My hands are shaking. Okay, volunteer to convene sessions. Do this. Anna Hogg, she's an amazing example of this. Anna was a rock star yesterday. She did 2 sessions in a row and another one this morning. She was phenomenal. She asked questions. She was just great. So be like Anna. Okay, and then if you want to comment on talks, your colleagues' stuff that gets published in the papers, in the media, and you see it, send me your name. If you're not on this list already, I can send this list to you. I did this in June. I got a list of female scientists that can comment, and I got a lot of people on that list, actually. So if you're in the media, send that to me. Send me an email and I'll send it to you. And it does work. This person here apparently was very motivated because she heard me speaking. I'm not really quite sure why, but anyway. She was obviously very happy. Final thing, I've only got 28 seconds to tell you about the new Scripps Polar Center. This is super exciting. I've been at Scripps for 20 years. This is my 20th AGU, shocking as it is. And we have just started a polar center. So things take time, but it can be done if you keep going. We've got beautiful logos, so we must be a thing. We have a building. Well, it's not actually our building. This is our wing of the building, we hope soon. Fiamma Stranio and I are co-located along here in our group, 2 groups, and we have a couple of other people that are joining soon. We have a cake that was made for a launch. This is where we are, so come visit. It's very exciting. Okay, I think I've got 12 seconds left. If you want to tweet about ISAT2, I have 2 ISAT2 pins for the first 2 people.
We have time for one question. Helen, do you want to take a question? Before? Anyone? Okay.
It's a great point. There's many people looking at that, and I agree with you, and I applaud you for consistently reminding us of that. It's fantastic. Thanks.
All right. I will also mention, since Helen brought it up, our Cryosphere section and our Cryosphere Executive Committee looks closely, at least once a year, on how we are doing with diversity through our award system and within our section. I will say that our male-female ratio is almost 50-50 for our 29 and younger, and we lose about 8% female every decade after that. Just so you have a little bit of an update on the statistics there. Again, our executive committee looks at that quite a bit. Please feel free to contact us. The people with the red snowflakes on their name tags. Next up, we have Dr. Ronald Kwok. Oops. Sorry, Ron. Give me just a sec. Ron hails from NASA's Jet Propulsion Laboratory. He was elected fellow for Cryosphere and Ocean Sciences section, which is quite an honor, for advances in remote sensing of sea ice cover of the Arctic and Southern Oceans. Ron has published over 110 articles in his specialty and has contributed to multiple NASA and ESA missions, including both the ISAT missions and Cryosat missions. I look forward to Ron's talk, Decline in Arctic Ocean Sea Ice Thickness, Volume, and Multi-Year Ice Covering from 1958 to the present. Please join me in congratulating Dr. Ron Kwok on his induction as an AGU Fellow.
So Helen showed most of the ISAT 2 results, so maybe at the very end I get to show just the sea ice part. Okay, so when I was invited to give a talk, I asked Laura what I should talk about, and so anything. So I picked something that's dear to my heart about ice thickness over the past 60 years, and not all of this is my work, but it's fun to talk about. And it sort of started, my work on ice thickness sort of started around 2004, and some of it's due to Jay Swally, who's sitting down there. In any case, about 12 years ago, we were at the completion of the ISAT 1 project, and I have this sort of 5 years worth of ISAT data, and that 5 years showed an incredible trend in ice thickness. There was an 1/8 of a meter drop in thinning over the entire Arctic Ocean. This is within the Arctic Basin. Doesn't include anything outside. But so I was wondering how to put this into context in terms of what happened before, to see whether that's actually reasonable. And obviously, for this particular 5 years, it was strongly weighted by the big drop in ice coverage at the end of summer in 2007 and 2005. And so there was, I didn't expect to see that kind of trend over that short period of time. So it turns out about a year before 2009, that was 2008, Drew published a regression, a multiple regression of all the submarine data that was collected within that polygon. That's where they could release all the submarine data, ice draft data. And so that regression sort of extended a quarter of a century back in time from the ISAT period. So we sort of put them together, and actually it made sense based on our understanding of the uncertainties in the regression analysis, as well as the uncertainties in the ISAT record. So that showed a drop of about 1.8 meters over that period of time. So an 1/8 from the ISAT period, and about a meter from about around mid-70s. And so that was sort of where we started. So now we have more data. We have Cryosat, we have Operation Icebridge, we have also all sorts of in situ measurements that are of interest. So this one, sorry. So just to put things into context a little bit before I talk about ice thickness, is that over the past 20 years or so, this shows the trend in the multi-ice coverage since 1999. And the multi-ice coverage is from QuickScat and ASCAT data. And we showed, so we started, say, at the peak of around 2005, I can't see it. So around 2005 or 2 or so, down to the present, So we lost about 2 million square kilometers of multi-ice in the Arctic Ocean. And also, so right now, the Arctic is covered by only about a third of the Arctic in the winter is covered by multi-ice. So that's a significant drop. So even the North Pole is now covered by seasonal ice. So this is sort of set the context of the types of ice thickness we see pan-Arctic over the past 10 years. So this particular slide goes back to 1958, and the reason why this was summarized, the thickness was summarized over 6 regions, was how the submarines sampled the Arctic. It's a buzz up here. How the Arctic sampled the Arctic over the 6 regions. And this was sort of picked by Drew Rothrock at the time. So there are 6 regions that covered the Chukchi, Beaufort, Canada Basin, North Pole, Nansen Basin, and Eastern Arctic. So we started at the North Pole at around more than 3 meters, 3.5 meters, and now we have, including the ice at period and the Cryosphere period, we only have about 30% of that thickness left. So we lost about 60% of the ice thickness at the North Pole. And if you look at the Chukchi Sea, can you imagine 2 meters worth of ice at the end of the summer in the Chukchi? Right now, it's probably mostly, there's a lot of open water in the Chukchi at this time. So this shows this sort of dramatic decrease in ice thickness in those 6 regions from submarine data, from ISAT, I keep saying ISAT2, and Cryosphere. So this shows that sort of drop, thinning almost everywhere in the Arctic. So this is what we've got. So putting everything together and adding to the what was published in 2009. So this includes airborne EM data, includes Operation Icebridge, and Cryosphere. So those are the 3 data sets added to the figure that we showed in the 2009 paper. So the AEM data, the airborne electromagnetic data, shows a nice decline. That's sort of consistent with what was predicted by the multi-regression analysis, as well as down to approximately the tail end of the ISAT period. So that's there. And then after that, we show this sort of, so there are 2 features in this plot to notice. One is, so between the submarine data and the ISAT data, there's this dramatic drop in ice thickness. And then after that, after 2005, 2007, it sort of flattened out a bit. So it's sort of varying around, in the winter, around 2 meters. And so that sort of coincides with the large decrease in multi-ice coverage in the Arctic Ocean, and it's mostly taken over by first-year ice. So this sort of, and one thing I didn't show here was if you look at the first-year ice in ISAT, the ISAT during the ISAT period, it also hovers around 2 meters. It didn't change that much. The big changes are in the multi-ice coverage. Is it me? So okay, so this is sort of, this shows the drop and then sort of the leveling off over this period. And just to, that's me. And that's, I just want to show that this, just to note that that's within that polygon in the Arctic Ocean and not for the entire Arctic. So this shows, with the satellite data, we can have, basically, we have almost pan-Arctic coverage, and we can calculate ice volume. And so this shows the ice volume changes over the period within the Arctic basin. And so this shows the big drop in ice volume associated during the ice age period, and then the sort of flattening off because the dominance of the first sea ice cover, because the first sea ice grows to around 2 meters every year, and the volume is just going to vary around this bit of the thickness and volume over time, over at least the short term. So I guess by now you ask probably whether there are any differences between ICET and CryoSat, and whether there's and why we think we can put them together. I mean, they both are supposed to produce estimates of thickness retrieval, and obviously that's difficult to quote a single number for uncertainty. But what I'll show you, the best we can do, is to look at the assessment of ICET and CryoSat retrievals using different types of in situ measurements. So one is the mooring data at the BGEP. This is the Beaufort Jai experiment moorings in the Beaufort Sea, and both of them are basically the BGEP moorings ice draft are common to both ICET and CryoSat, and they're both within 1/10 of a meter, and so they shows you that over the period at least in those areas the retrievals are consistent, as well as the submarine data. We can look at the submarine data when we have them during ICET and CryoSat, and they're also within 1/10 of a meter. And also the other sensors as well, the other ice draft measurement as well. Now the variability is a little different from one instrument to the next instrument, but I should also note that the variability in these comparisons includes the uncertainty in measurements from these other instruments, as well as the time-space differences between the actual in situ measurement and the satellite measurements. Because when we compare these things, we have to put them together, and they don't always sample at the same time and same space, because they're always off a little bit in time and off a little bit in space. So the variability is associated with that. So this is sort of the best evidence that we have that what we have is reasonable. I mean, obviously we can't have extensive validation of these remote sensing measurements over the entire Arctic, because that's too expensive and logistically impossible to do that kind of validation. So this is represent at this point at least my best estimate of the trend and the of ice thickness over the Arctic Ocean between 1958 and present. So one other thing I want to point out is the correlation between ice volume and multi-ice thickness. Now this is for the entire Arctic basin. So they're highly correlated. So the red is the entire time series of multi-ice coverage, and the blue is the ice volume time series from ICET and from CryoSat. So the multi-ice coverage explains about more than 80% of the variance in ice thickness over this time period. So if you look at the ice volume time series, if you just look at by itself, they sort of look discontinuous. But if you look at the correlation between two curves, so it sort of makes sense, and it lends credence to the claim that these measurements are reasonable and consistent. So this is the correlation, and this is the R squared for the two curves. So there are two. If you detrend the two curves, there are two extremes in the variability. One big extreme is the big drop in ice volume after the summer of 2007, and the other is there's this increase in ice volume in 2014, and that's associated with a cooler summer and a significant ice convergence during the summer of 2013. Now, the question is whether it's ice convergence that's causing the cooling, or whether it's the actual cooler summer. I think what the data suggests is ice convergence has a lot to do with the cooling during that summer. So here's where we are and let's see. I want to say this first. So these are summary remarks before I go on to ISAT2. So this is, I think I said all this stuff. So I guess the last bit, the important thing that I want to say is this new normal in the Arctic is dominated by fast-growing first-year ice with an annual growth of about 2 meters, and that's why that's why the ice thickness is sort of hovering at around 2 meters at this point, and this is a new normal. I think the new normal term came from Martin or Don Perovich, one of them. Maybe Jackie will correct me. But I think this is sort of a transformation of the Arctic into from a perennial ice-covered Arctic to one that's dominated by behavior of seasonal ice, and I think that's a significant thing that's been pointed out by a number of investigators. So here's where we are in terms of thickness within the polygon in the Arctic Ocean, and we will have so now we have ISAT. So I think Helen showed this already. It was launched on September 15th, and I was there. It was kind of cloudy, but I saw a blip and then it was gone. But I think the incredible thing about ISAT is the resolution and the precision of the sensor for doing the types of things we want to do over the Arctic Ocean. The footprint is 17 meters, and it repeats itself every 70 centimeters. So that gives us significant sampling of the and resolution of the ice cover that we're looking at. And it has 6 beams. The 6 beams, it gives us significant advantages in looking at variability, and also we can probably go in and find the ice flows, individual ice flows, and figure out the ice flow distribution in the Arctic Ocean or even the Antarctic. So this is where we're at in terms of, so we're about 3 months from launch, and we're 2 months from start of collecting science data, and this is our first freeboard map of the Arctic Ocean that's constructed using data from 2 weeks worth of ISAT data. This is from October 14th to October 28th. And most of you are familiar with this projection. There's thicker, higher freeboard on the Greenland side, and which thins to the Siberian side, and some very, very thin ice, or very, very low freeboard ice just around the ice edge, and that's associated with the growing ice cover. So that's one exciting thing. And the other exciting thing is about the Antarctic, the Southern Ocean. Now, we know a little bit more about the ice thickness of the Arctic Ocean, but not as much and we want to know a lot more about the Antarctic, and we don't have a very good estimate of the Pan-Antarctic thickness of the Southern Ocean. So this is another first freeboard map of the Southern Ocean from ICET 2. And we can see the very, very thick ice, or the thicker ice, or the higher freeboard ice in the Weddell Sea, and as well as the Bellingshausen and Amundsen. Typically it is thick here and it drifts out toward the Ross Sea. And most of the Antarctic is pretty, the freeboard's relatively low. So we have a multi-beam sea ice products, and you guys should use these products. These are great products. I think the sensor is doing, the LiDAR is doing a great job, and I think I'm out of time to get out of town. So I think I'll stop here.
We can take one question for Ron. Is there a question? All right. I have been asked to announce 2 things. So the 100 Years of Cryosphere session following this will be in Salon H. We do not expect everyone to get a seat. Note that will be also broadcast through the AGU Go, and you can submit questions for the panel over the social media channels that will be monitored during that. So if you choose to get a beer as opposed to a seat, don't worry. You can still see that. The reception this evening, the Cryosphere reception, is at the Grand Hyatt Independence A West, Corridor A. If you were a government employee who may not have been able to register because of shutdown chaos, there will be tickets available at the door, and AGU has said that they'll make sure that you can get in for that. All right, and now on to our main event. The 2018 Nye Lecture is awarded to Dr. Jacqueline Richter-Mengy from, this will take me a minute to get all these right, the U.S. Arctic Research Commission, the University of Alaska Fairbanks, the U.S. Army Corps of Engineers, Cold Regions Research and Engineering Laboratory, and Dartmouth College. Jackie's long list of affiliations exemplifies why she was chosen as this year's Nye Lecturer. Jackie was chosen for her contributions to Arctic and sea ice research and her ability to transform that research into public knowledge and government action. Her efforts throughout her career have been monumental and culminated in a presidential appointment to the U.S. Arctic Research Commission. Jackie's research has given us a more comprehensive understanding of the Arctic. She has participated in more than 20 field programs. Recently, she has overseen the design and development of a network of autonomous sea ice mass balance buoys as part of the Arctic Observing Network to document and understand the rapid changes in thickness and extent of sea ice cover. She serves as an editor of the annual report on the state of the Arctic Report Card, through the NOAA Climate Program Office. It summarizes and presents the most recent observations collected by the international community on the physical environment. Throughout her career, Jackie has mentored and served as a beacon for students and early career members of our community. I once heard Jackie described as fierce, and I must say that she truly is. Jackie fiercely protects scientific integrity, fiercely distributes information, and fiercely serves both the civilian and DoD branches of our government. For those of us following in her wake, I give you the following advice. If you are ever in a government meeting about the Arctic, in either the DoD or civilian agencies, say that you know Dr. Jackie Richter-Mengy. Her excellence in all that she does has enhanced our community's reputation across our government. I look forward to hearing her talk, A Career of Change. Please join me in congratulating our 2018 Nye Lecturer, Dr. Jackie Richter-Mengy.
Well, thank you very much for that kind introduction. I would guarantee my girls will tell you the one characteristic they agree with is fierce. Along the way. Oh, well, thank you very much. Thanks very much. Can you take that? Thank you. But give it back to me at the end, please. So I'm really grateful for this honor. I can tell you through my career, the honors that mean the most to me are the honors that I just don't see coming my way. And this is certainly one of them. I've sat in many NI lectures. I never really visioned myself on the podium, but here I am today, and I hope to live up to the honor. I do want to take a moment as I figure out how to move things ahead. How do I, just click? Okay. I do want to take a moment to remember the person for whom this lecture is named, Dr. John Nye, who is still practicing. He is recognized in this lecture for his seminal work on glacier flow, giving us a better understanding for how glaciers move. He is actually still a professor emeritus at the University of Bristol in the UK, and he's still publishing, which is amazing. His latest paper is published in 2018, so he is still going. I also want to remember that this is AGU's 100th birthday. It also gives me a chance to wake you up. I will keep this with me in case I see you nodding off. But birthdays and anniversaries tend to put you in a mood of reminiscing. And indeed, when I was thinking about the abstract for this talk, I started reminiscing about my career. Now, it's not 100 years, though some of you may wonder. It's almost 40 years, though, of accumulated experience in studying the Arctic sea ice cover. I started in 1981, and here we are in 2018. Now, you've heard my affiliations, but most of my career was spent at the Cold Regions Research and Engineering Laboratory in Hanover, New Hampshire. I arrived at CREL in 1981, fresh out of the University of Delaware, go fighting blue hens. And I had a degree of Master's of Civil Engineering with a specialty in soil mechanics. So I came with that in 1981 and was introduced quickly to somebody who was doing ice mechanics. And I again started studying the Arctic sea ice cover, but had a variety of different perspectives. Oh yeah, one thing I should do, okay, so everybody's probably wondering how I've made out over these 40 years. Well, thanks to hats and scarves and big parkas, I don't think there's been much change. So with regard to my career, when I first started out, as I mentioned, I was doing ice mechanics. That work was being applied to the development of offshore drilling capabilities north of Alaska. We needed to know what the engineering properties of the sea ice cover were in an effort to build structures that wouldn't move off of their foundation. That work went on until the price of oil dropped. And then it just didn't become economically viable to continue this work. So I changed my perspective to working on the support of the Navy operations in the Arctic. That work went on until there was less stress between, at the time, the Soviet Union and the United States, so glasnost. But at that time, to my good fortune, we started noticing that the Arctic was being affected by the warming climate. And so that became really where I've spent the rest of my career, is making observations about how the Arctic sea ice cover is being affected by the warming climate. Now, with that change in application, I really have had a change in perspective. When I first started, my perspective was about this big. I would go to the Arctic, take core samples of ice, 25 centimeters in diameter, bring them back to the laboratory, test them in compression, tension, confined compression, to look at how the engineering properties changed as a function of things like ice temperature, porosity, and crystal structure. But even with not just the application, but being in the Arctic and being a person who really likes to solve mysteries, flying over the Arctic, I began to look at this ice cover that's so mobile in nature. You would see cracks forming, leads we call them, or ridges coming back together. And you just had to wonder, how did this happen? What were the forces involved? Why did a crack happen here? Why did a ridge happen there? So my perspective moved from these small cores of ice to looking at the sea ice in a system, at a system level. And I've spent my career, again, with boots on the ground largely. We've heard a lot about remote sensing. My work has really had me out on the ice cover looking at what's going on. And there certainly has been change. You've already heard about that today, some theme that continues through. We look at the extent of the summer sea ice cover in 1980 compared to 2018, and it's vastly different. Satellites have done a great job of monitoring this change. I do want to remind folks that the sea ice cover changes in its extent through the seasonal variability. Right now, the Arctic is dark and it's cold, and the sea ice cover is growing from the Arctic basin out into the peripheral seas. It will reach its maximum in March. At that point, the seasons begin to change, things warm up, the sun comes up, the sea ice cover will retreat from those peripheral seas into the basin in the center. We tend to look at what's going on with regard to the winter maximum in March and the summer minimum in September. And if we look at the history where we have satellites available to us, we see here what that trend is. You'll see a lot of variability from year to year. That's expected. The forcing changes just like our weather does in any given year. But we're looking at the downward trend. And that downward trend is undeniable, whether you're looking at the winter or the summer. The summer is certainly more pronounced. If I did this for every month in the record, you would see that every month is decreasing, but again, the summer is most pronounced. So we hear a lot about the extent, but we've now just heard, thanks to Ron, a lot about the thickness. And this has been a more difficult problem in monitoring how the sea ice thickness has been changing with time. Ron showed in little tiny pictures, but I'm going to show a bigger picture here, what the variability of sea ice is as far as thickness goes in the basin, and it really reflects how the sea ice moves around in the basin. So we tend to have let me get this right, talk about technology change, there we go. We tend to have the thinner ice that's here along the Eurasian coast. This is from Cryosat data. In the last 5 years, this ice tends to be thin. It says, Ron said, this is your seasonal ice that's growing new every year. And here along the Canadian archipelago and Greenland, we have a thicker ice cover where the ice is converging against the coast thanks to the Beaufort Gyre. But it varies widely. Still the best way, the most accurate way to get a measurement of ice thickness is with a drill. Because you drill down through the hole, you put a measurement, and you can get something within a few centimeters. But you can't get much spatial coverage. So thanks to the advent of satellites with their altimetry capabilities, and here you see another picture of ICET2. Again, there's some definite themes through these different talks. Launch of ICET2. I wasn't there, but I hear it was great. But if we look at the data that are available to us from satellites with regard to thickness and knit the data together, what we see is over the years, over this 24-year period, there's been a decrease in thickness on average of almost 5 meters. So not only is the ice cover changing in its extent, but it's also changing in its thickness. We get a little bit longer look at things if we use another product called the Sea Ice Age. This is also derived from satellites, though in a different way. We're looking at identifying locations of pieces of ice, watching them drift around the Arctic basin. And the connection here is that the longer a piece of ice is in the Arctic Ocean, the thicker it's going to be. And you can actually see the exact same distribution we just saw from the satellite data. Thinner ice along the Eurasian coast, and thicker ice along the Greenland and Canadian archipelago. In this particular case, the blue, get it over here, is 1-year ice, and outside the red is 5-year ice. Now this adds about 10 years to the record that of looking at it, and you can really see, again, what Ron just emphasized how much the ice cover has changed. This is 1985. This is 2018, both in March when the ice cover's about reached its maximum thickness. And you can just see from the red color here how prolific the older ice is in 1985 compared to what it is in current day. And here's a time series, again, with this incredible drop in the volume of the older, thicker ice. And as Ron has already pointed out, this means that we have a younger, thinner, more vulnerable cover subject to the summer melt. Now, that's remarkable, the satellite data. But what's been most remarkable to me is that in the almost 40 years that I've been observing the ice, I've been an eyewitness to this change. I did a little plot of where my major field programs have been over time, and I found out I don't get around much. So, but that has its advantages. All of my major programs have been in the Beaufort Sea. To give you a sense of orientation here on this drawing in, this is the north coast of Alaska. Here's Utqiagvik, formerly known as Barrow, Banks Island, and you can see that all my work has been in the Beaufort region. So these are two bookends from my field programs. 1982, when I was out collecting ice samples for doing the engineering properties of ice, we wanted to get the thickest multi-year ice. So this is ice, again, that's grown multiple years. And my field notebook, we're only 25 miles off of Prudhoe Bay. From my field notes, contained a wide variety of multi-year flows and was convenient to Dead Horse, Alaska. You can see the big flow that we aimed at right here. Again, the thicker the ice is, the higher its freeboard, so you can actually see this ice is higher than the surrounding ice, so this is showing that it's thicker. You can also see that it's kind of rounded. That's because it's gone through summer melt seasons. So let's fast forward to my most recent trip to the Arctic, which was in February of 2018. I was helping pick an ice flow, a multi-year ice flow, that would be home to the U.S. Navy Ice Camp Skate. The Navy every 2 years goes up to the Arctic, establishes an ice camp to support submarine operations. They're practicing working in the Arctic. We're 200 miles off the coast of Alaska before we ever even saw multi-year ice. Field report, lots of thin and fractured first-year ice on the way to the identified multi-year ice flows. Options for the ice camps are limited, and they were hugely limited. Let me just blow this up a little bit more so that you can see what the difference that I've been seeing is. Here's 1982 March, and here is February 2018. Both of these are within a few tens of miles off of Prudhoe Bay. You can see the difference. I can see the difference. It is undeniable. And the reason that we have that difference, you can see here again going back to satellite products. Look at the Beaufort Sea in September 1981 summer versus September 2017. In 1981, the Beaufort Sea in the summertime was filled with thick multi-year ice. Current day, it's opened ocean. So when the ice grows back, it's this thin first-year ice that, again, is very mobile and changes quite frequently. So that was kind of my perspective on sea ice. I became involved with the Arctic Report Card in 2006. And it wasn't so much that I didn't know that there were other stories out there. It was that I really hadn't had to read the papers. But as the editor, I had to read the papers of what else was going on. So my perspective began to broaden up with regard to the other indicators of climate change or effects that were going on. Now, I want to point you to the Arctic Report Card. It was actually released just a few hours ago for 2018. I hope you'll have a look at it this year. I think there are 14 different essays on different environmental changes in the Arctic, set in the context of a historical record. But we see the Greenland ice sheet. The mass of the Greenland ice sheet is decreasing. We look at surface temperatures of the ocean and the peripheral seas that are now more exposed in the summertime. There's a tendency for there to be warming. The changes in the ocean surface temperatures as well as nutrients are affecting where fish are in the Arctic. We're actually seeing a northern migration of fish. This example's in the Barents Sea, where Atlantic fish are moving northward. They're very adaptable, so they're actually moving north at the loss of the Arctic fisheries, because Arctic fish aren't as adaptable. And we're even seeing the connections with regard to the lower 48, so-called, because we're getting more and more evidence of the warming Arctic affecting the jet stream, which moves weather across the continent. It also moves weather across the globe, but since this is a US meeting, I'll stick to the US. And we're getting a linkage to these more extreme and frequent storms. So that's kind of the environmental change that I've seen. It's undeniable that the Arctic is undergoing a lot of change in many different ways. But there are other changes that I've witnessed in my career. The change of technology. Believe it or not, for you out there, in 1981, my first manuscripts were handwritten. It was not that Krell didn't have computers, but we didn't have computers on our desk. The computer was downstairs, so you hand wrote your manuscript, you took them downstairs. Somebody in a typing pool would type them up, put them on the computer. They would come back to you and correct, and you would iterate until it was time to actually submit your paper. I'm happy to say now I do use a computer. I've given up the handwriting, but it was a different time. It was a slower time. And there's something to be said for the slower time. There was a little bit less challenge in time management. If I went to my mailbox and I had one letter a day from a colleague, it was a big deal, right? Imagine my email if it was all hard copy. I would have to take a wheelbarrow back and forth to my office, and the expectation is I would be answering every single one of those letters every day. It just is a lot of challenge with regard to time management. But there's some really good things too. And that is how the advent of the computer has really facilitated our ability to collaborate. And I'm just going to use one example here of one of the collaborations which you can join. That is the IARPIC collaboration. So you might ask, what is IARPIC? It stands for the Interagency Arctic Research Policy Committee. It is a committee of the US federal agencies, 12 in total, who have a responsibility to do work in the Arctic. Now, I'll talk about the Arctic Research Plan in a few minutes, a little bit more detail, but the IARPIC is responsible for developing the US Arctic Research Plan and seeing to its implementation. But they don't want to do this in a vacuum. They really want to be hearing from the community of experts, from stakeholders, from members of the indigenous community. So they've created this thing called the IARPIC Collaborations that opens the door to everybody else. And the IARPIC Collaborations has currently 9 collaboration teams. A person can join 1 to 9 of these depending on your interests. And imagine this, with joining, which takes just a minute, you can suddenly be in contact with over 1,500 members of your community without leaving your desk. I don't know about you, but I get tired of flying on an airplane, and I get sick almost every time I do. So this is a really nice option for me. It's a great way to meet other researchers, to find mentors, program managers. You can hear what they're doing and what they're thinking about, and also make links to the indigenous community. I would highly suggest you join this. It has been a boon to me as well as many others. Now, I'm thinking about the IARPIC collaborations. I also remember that my perspective has more recently expanded with the appointment to the U.S. Arctic Research Commission that was just mentioned. The commission is small but nimble. We're small enough that we actually get some things done. The commission, there's 7 named commissioners. The director of the National Science Foundation is an ex officio commissioner. We're led currently by Fran Ulmer, who just has an incredible depth of knowledge with regard to the Arctic, and in particular, the state of Alaska. So as I mentioned, there's a connection between the IARPIC and the U.S. Arctic Research Commission. Both of these entities were established in 1984 as a result of the Arctic Research Policy Act that was put in place by the U.S. Congress. The role of the commission is to come up with goals and objectives for the Arctic research program in the United States. Informed by those goals and objectives, the IARPC then develops the U.S. Arctic Research Plan. To give you a sense of the goals and objectives, which we're updating now, these are updated every 2 years, they include observations of the environmental change that's going on in the Arctic, the health and well-being of the native community, infrastructure, and also encouraging international science and research collaboration. To give you another sense, so we do the goals go to the research plan, and that information helps inform Congress about how to appropriate funds to support Arctic research. So imagine this, a person that started out with a 25-centimeter perspective on Arctic sea ice cover is now helping to develop the Arctic Research Plan. Just kind of amazing to me. But even more gratifying being part of the commission is the opportunity to engage with the local communities of the Arctic. Most recently, in September, we visited the Northwest Arctic Borough, working out of Kotzebue, but we got a chance to fly to some smaller communities. This one, Selawik, Alaska. You can see Fran there on the right-hand side talking to the local community. On the top left here, you can see this small community, again, 350 people living on this river delta. There is no question that these people's lives are being affected directly by climate change. And there's another thing that I suggest that you sign up for, another freebie. This is like getting swag, if you will. This is the U.S. Arctic Research Commission's Arctic Update. It's done almost daily. It kind of compiles all the times you'll hear about the Arctic in the news media and also meetings that you can go to. So sign up for this too, it's a great deal. So there have been other changes, and Helen even pointed this out. Change in gender diversity, and I'm going to speak specifically about the number of men and women in the science. Okay, on the left, here I am out in the field in the right around 1990. I'm circled there. I was 200 miles out in the Arctic, so I can genuinely say I was the only woman around for hundreds of miles. Okay, come to a meeting in Ukjavik in May of 2016. Here I am again, but wow, look at the difference. 50% women. It makes a difference when you're not the only one of a certain kind. Now, 50% is pretty unusual when it comes to the balance of genders. So looking here at just our own cryosphere section, and Laura's already mentioned some of this, more typically you have a distribution of about 25 to 30% women balanced by the percentage of men. Progress is being made, but progress won't truly have been made, in my mind, until we actually reflect the US population, or the population of the world. That's more 50-50. And as Laura pointed out, if you look at the little circles here, we have more students, but as we get older, there's an attrition. Why is that happening? Study after study says that it's happening because of the workplace environment, or that's a big reason why it's happening. This particular study looked at researchers in the field because there was a feeling that field situations might present an even more challenging environment. But as it turns out, these results are pretty consistent with any work environment. I want to point you to these first two columns. On the left is the size of the survey sample, about 650 people, men and women. The next column over is how many of you, the question was asked, have either experienced directly or indirectly sexual harassment. There's not much change in the density here. Harassment happens, and it happens often, and because of this we get attrition, because often this harassment is happening to new entry-level people, and they just don't want to work in an environment that's not welcoming. What's the consequence of accepting the status quo? You're basically agreeing to leave brains on the table when we have some incredibly challenging problems ahead of us. We're losing capacity and talent when we accept this status quo. The good news is there's a number of studies out there that we can be working towards better equality. Studies will show that role models make a difference. In this particular case, they were studying the retention of young women in the geosciences as a function of role models. And you can see the data there is very convincing that it makes a difference if a young female engineer or scientist has a female role model, they'll stick with it. Other good news came out of the National Academy of Sciences report just issued in 2018 about sexual harassment with regard to scientists, engineers, and folks in the medical profession. What that report says is that the tenor, the mood, the tone of the work environment is one of the best ways to measure whether you've got a problem with sexual harassment, the culture of the work environment. That means institutions can actually change the culture to make it more welcoming. And that's changing a culture with more civility and respect. And the end result is a healthier environment for everyone. We all win. Nobody's losing in this particular game. Related to the changes I've seen with regard to gender diversity is the role of the indigenous members in our research. On the left is a shot of the group that kicked off the Arctic Report Card in 2006. I don't even have to look far back. I'm in the middle there, and I have to say I've not done much in my career to move this needle forward. When it was time to put together the team for the Arctic Report Card, I am really disappointed in myself to say I didn't even think of inviting a member of the indigenous community to join us. Fortunately, there are other people in our community who are doing a better job than I've done in involving the indigenous community. And when you think about it, it makes a ton of sense to involve the indigenous community. I mean, we observe the Arctic out of largely curiosity. I mean, there's applications, but when I go to the Arctic, I mean, I actually travel to the Arctic. I don't live in the Arctic. I observe the Arctic, but I'm not there. You look at members of the indigenous community, their observations and understanding of their environment are literally a matter of life and death. They are highly motivated to understand their environment. Just look at this picture of whaling in Utqiagvik. You've got people standing on the edge of the ice cover. Heck, on the bottom right, you've got a whole community of people standing on the edge of the ice cover retrieving this whale. You get error with regard to the thickness or how the ice is moving, you're going to have a loss of life of yourself, your crew, potential catastrophe with regard to community. And I am not overstating this. And here's just a vignette. If you came to me, I have spent my life studying the thickness of the ice cover. If I was sitting in a room next to an elder, and you came into the room and you said, I want to know what the thickness of the ice cover is, guess who I would tell you to go talk to? Not me. I would point you in the direction of the elder. That's how much confidence I have gained in working with this community over what their capabilities are. And you see on the left-hand side a great study where there's a combination of researchers from the University of Alaska Fairbanks, the National Snow and Ice Data Center, and members of the community at Utqiagvik who are actually working together to measure the thickness of the ice cover of these whaling trails and monitoring those over time. Working with the indigenous community, you learn that there's just a different way of thinking. You don't need to look at all of the words on this. I just want you to look at the shape of these illustrations. They're both circular. On the left is a description of indigenous knowledge, in particular food security. On the right, co-production of knowledge, again, where we're trying to pull together indigenous knowledge and also Western science. They're both circles. Circles are inclusive by nature. Again, this is thinking about the environment as all parts are important, all parts are equal, and you are part of the environment. Contrast this with the scientific framework we typically see. This is an example from the Search Study of Environmental Arctic Change. It's linear. If I was going to draw a picture of my field program, I'd have little boxes and arrows. Maybe I'd have a circle if there was a feedback, but we tend to think of things more linearly. And I'm not saying that one way of thinking is better than the other, I'm just pointing out the difference. And there is a challenge when you have different ways of thinking of bringing that together. But study after study will show that the more diverse, the more inclusive you are in developing your program and executing it, the more chances you are of being successful. Now, I was really pleased to see when I got online, when I was preparing my slides to get an update of what was going on with search, this is the picture that I saw, the illustration. It's a circle. Evolution. Perhaps our ways of thinking aren't so far apart, or we're working hard to make them be synergistic. And again, I would urge people, I wish I had more time in my career. I'm going to make maple syrup on a farm. But anyways, I would urge you follow the path of some of the colleagues that are here with us today in working more closely with members of the Indigenous community from the beginning of your programs, not the middle and not the end. It requires a deliberate engagement, respect, trust, and equity, but the results are going to be better. Now, I'll end with one thing that hasn't changed through my career, and that's the importance of a network. In my little world, I have had certainly a number of colleagues that have helped me along the way. I've had mentors all along the way who have been hugely important. I mean, again, I came to Arctic sea ice having studied soil mechanics, so I needed people to help me learn about the Arctic. I'm getting mentored even now. As a new member of the Arctic Research Commission, I'm mentored by the other commissioners as well as the staff that are there. And it's always fun when you're, instead of being mentored, you're the mentee. Working with students has been huge and really rewarding. But that's just part of the network. The other network are the technicians that I've worked with over time who've helped develop instruments, seen to my safety in the field. My husband will tell you I'm probably not the most talented when it comes to mechanics. So the technicians have been huge. The office staff, everybody should follow this rule. Don't get on the wrong side of your office staff. They're the people who get stuff done. And of course, there's family too. Whoop. So I have learned through my career that it takes a network to support a career, and I've also learned that diversity and inclusiveness matter. You need to work hard to see that your team is welcoming and includes a variety of different perspectives so you get a really full picture of what's going on. And I want to thank those of you who are in my network. You've seen a lot of names here, people that helped me put this talk together, and people who have supported me through my career. I'll end for some questions with this picture, dedicating the talk to the next generation of polar researchers, their teachers, mentors, and models. This is a picture of my daughter, where I visited her first grade classroom and exposed them to what goes in the Arctic. And I'll tell you what, we talked about whether polar bears and penguins were in the Arctic. And the next time I visited those children, they said to me, "Miss Mengi's mom, there are no penguins in the North Pole." And I was, yay, they're sponges. So you can't start too early. Thank you very much.
Jackie, thank you so much for that talk. Questions for Jackie?
Don't be shy.
And if
Look
not,
what I
I'm gonna throw one out for AGU Centennial, and that is throughout your career, and even if you want to go back 100 years, what do you think the most
Well, that's not
important?
that far
I
along
know
for me right now.
the most important advance or contribution that sea ice science has made.
I would say that one of the most important contributions sea ice has made over the years is to really be a strong indicator of the change that we're seeing with regard to the climate. I mean, even going to classrooms like this, if you ask a child what happens to an ice cube when it melts, or when it gets warm, they'll tell you it melts. So it's very visceral, very convincing with regard to what we're seeing in climate change. So,
Any other questions?
we're done?
All right. Thank you all for attending the NI lecture.